Welcome back. Today, in the last lecture, we talked about the kinematics of rotational motion about a fixed axis as different from that of an individual particle. So today we'll talk about the dynamics of rotation about a fixed axis. But before that, I will just make some amends about class 52. I have received some comments from one of the viewers, Mr. Tawsif Ahmed, and he asked a couple of questions regarding the presentation. I have to admit that there was a gross mistake about the theorem of parallel axes. I stated and I proved the theorem of parallel axes again for a lamina like I did for the theorem of perpendicular axes. But this theorem actually applies to any body of any shape, and it says that if there is an axis which is passing through the center of mass of system of that body may be spread. Okay, so there is a point which is the center of mass of the system or the center of gravity of the system, and then if we want the moment of inertia to be calculated about any parallel axis a distant r from the axis which is passing through its center of mass, then of course the equation is the same, that the moment of inertia that we calculate is equal to Ig, the moment of inertia about the center of mass, plus mr square, where r is the distance between the two axes. Okay, so I correct myself. I insist that theorem of parallel axes is for a body of any shape or size. Okay, and then we read it as follows: the moment of inertia of a body about any axis is equal to the sum of the moment of inertia of the body about a parallel axis passing through its center of mass, and that is this, and the product of its mass and the square of the distance between the two parallel axes. So this is one of the things which I wish to admit in this lecture. Correction is there. Then in one of the figures, in one of the diagrams, where I had taken 2 points C and O, and there Mr. Tawsif, he wanted to know whether the center of mass lies within the body, inside the body. Yes, it is. But in some of the cases, the center of mass is not within the body. Okay, there are special cases of donut type systems where the center of mass is not inside the body. But anyway, the case that we have taken there, the center of mass is inside, and O that has been taken, that has been chosen, is the origin of the chosen coordinate system, where the axes are parallel to the axes that we have shown passing through C. So they are parallel set of axes, and O is different. It's our choice, doesn't matter where we choose it, because this I is equal to Ig plus mr square is going to hold whether we take it on one side or the other side, but the axes associated with C and O, they should be parallel to each other, x, y, z, x dash, y dash, z dash. There is another thing which I want to emphasize, is that while the derivation we were making, I took the distance of the point P from the new axis under consideration as r plus x. Squared it, and thereafter we carried out the mr square and mx square and this and that for the torques that are applied there. We could, of course, take the position of the point such that it's instead r minus x, and then we square. And so we get r square is equal to 2rx plus x square, and r square is equal to r square minus 2rx plus x square. Now, the contribution of this term or this term here, this contribution turns out to be equal to 0 to the torque, and the only contributors therefore are the r square and x square respectively, r and x respectively. Okay, so it doesn't matter. I could take that value of the P as r plus minus x, r plus minus x, and proceed and obtain the same results with the arguments that are already given in lecture number 52. One thing more I want to add, that if I have this equation and I and mr square, mass and the r, they are given to us. I, which is the moment of inertia about any axis, is given, then of course we can calculate Ig as this Ig will be equal to I minus mr square. In the dynamics of rotational motion about a fixed axis, we will talk about the work done, and we know that work done in translational motion is given by Fdx, and that in the rotational motion about an axis is given by torque into d theta, where dx and d theta are the displacements, the linear displacement and angular displacement respectively. Before we further this, there are some issues that we must talk about the fixed axis. So fixed axis, I make clarifications with the help of a discussion. The first item that I want to tell you and share with you is that when there are torques working and the work is being done, etc., and the motion takes place, then only those components of the torques which are along the direction of the fixed axis, about the direction of the fixed axis, they need to be considered. Because only these components which are along the direction of the axis, fixed axis, can cause the body to rotate about that axis. So this is the axis, and if the components, they are also along this axis, then they will be able to make the body rotate about this fixed axis. So there is a component along the fixed axis. The second item that we need to consider is that any component of the torque which is perpendicular to the axis of rotation, what it will try to do, if the component is perpendicular in this direction, then what it will try to do, it will try to shift the axis of rotation, from its fixed direction okay, fixed sense. So I write that any component of torque perpendicular to the axis of rotation will tend to turn the axis from its position, which is not desirable. Now, let us say, if we want to hold the axis in its position, okay, and if the axis is held in this position, the axis of rotation, the effects of perpendicular torques must cancel out each other, must cancel out, so that they need not be considered. Because they cancel out, therefore we are not going to consider them. So what we are going to consider them is the components of the torque which are in the direction of the axis and not those which are perpendicular to the direction of the axis, because they tend to cancel out each other. So therefore only forces lying in the planes, now I'm talking about forces which give rise to torque, okay, only forces lying in planes perpendicular to the axis. If the axis is like this, then we have planes which are perpendicular to the axis, and if there are forces lying in the planes perpendicular to the axis, we must consider them, and we must not consider the forces parallel to the axis. If the forces are parallel to the axis, of course there is no contribution to the torque, desired torque. As you can see, R cross F is the definition of torque. R cross F is the definition of torque. This is a cross product. The product is torque, and as per the definition norms, we know that this new vector must be perpendicular to this vector as also this vector, so that the dot product of the two, torque dot R and torque dot F, these two dot products must be equal to 0. So this is, in a nutshell, I am going to continue with this discussion, but these are certain things which are desired to be discussed, to be clarified for the dynamics of rotational motion about a fixed axis. So we must realize that the dot product of R with torque or torque with R, they are equal, and therefore we need consider only components of R perpendicular to the axis. Okay. Now I have a cross section of the rigid body in which a particle is undergoing uniform circular motion. Because it is cross section, therefore my axis of rotation is perpendicular to the board, out of the board or into the board, doesn't matter. We find that we take a particle P1 at this location, and it makes an angle theta with an axis which we write as x dash, and it traverses the path from P1 to P1 dash in traversing an angle of d theta here in a given time interval. So Cp1 we take as equal to R1, and at this point, this is in the x dash y dash plane, a circular path for the particle which is undergoing rotation about a fixed axis. This is a part of the body. This is a cross section of the rigid body. The circular path we are taking, the direction, there is a velocity vector which should be in this direction. I have this R dash, R1, this line is extended like this, and we apply a force F1 corresponding to it in a direction which makes an angle alpha 1 with this direction. Okay, F1, I have shown it here. Because the velocity vector is in this direction here, therefore this makes an angle of 90 degrees with this radius vector, because they are perpendicular to each other. This is tangential to the path over here, and this is radial, and the angle between the radius and the tangent is equal to 90 degrees. So let us call this angle as phi 1, which the F1 makes with the velocity vector. Okay. So with this, if it is clear to us, then we have the displacement of the body ds1 from p1 to p1 dash, which has been shown over here as the displacement of the particle. Now let us see as to what is the correlate. F1 is perpendicular to the z-axis. The z-axis is out of the board. Okay, so any line passing through this and on this plane is going to be perpendicular to the axis. Okay, the axis of rotation. So F1 is perpendicular to the z-axis, and dW, therefore by definition the work done will be equal to F1 dot ds1, which I can write as the magnitude of F1 multiplied by the magnitude of, because this is a scalar, so this quantity should be scalar. This is dot product, it is also a scalar product. So this turns out to be equal to F1 ds1 cos of phi 1. Okay. Now ds1, as you know, that this is an arc, therefore this can be written as equal to r into r1 into d theta. Okay, this must be written rather as r1, okay, r1 d theta. So this is r1, and cos of phi 1 is the same as sine of alpha 1. So we substitute that and we get cos of phi 1 is equal to sine of alpha 1, ds1 is equal to r1 d theta. R1 and R one same thing, so it's better that we take R. This is R, the radius is R. Okay. So we have this value for the dW. Of course, phi 1 is the angle between F1 and tangent, and alpha 1 is the angle between F1 and CP1. So after these definitions, let us calculate the torque about due to F1, the force about the origin. Okay. And this will turn out to be OP1 that we had in that figure cross F1. But we can split OP1 in two parts. One is OC and the other is CP1. The sum of the two vectors is equal to the vector OP1 cross F. But you see that this OC is along the axis of rotation. Okay. So we exclude the torque due to OC. So effective torque becomes equal to torque 1 is equal to Cp cross F1, which means that the magnitude of the torque is taken as tau 1, which is R1 F1 sine of alpha 1, which we have obtained here. So dW is equal to torque 1 into tau 1 into d theta. But the d theta is the same same for all the particles which are rotating together, and therefore for all the torques that are there we can sum them up as scalars. Tau 1 plus tau 2 plus and so on. So dW becomes equal to the sum of these, which is tau into d theta, which is similar to dW is equal to the work done is equal to force into the displacement in the direction of the force. So picking up from power, from work done, we define the corresponding power. Okay, by definition you know the power is the ddt of work done, and I write it as dW over dt, and this is equal to torque multiplied W is equal to torque into theta. So I can write this, rearrange and write this as torque multiplied by d theta over dt, and so we get that the power is equal to torque into the angular velocity, just like we obtained for power calculations in the case of translatory motion as P is equal to Fv. So this is the instantaneous power that we have obtained. Now let us take, to wind up this, dynamics of rotational motion about the fixed axis, let us define the kinetic energy of rotation, which is just like its counterpart half mv square. We write it as half I omega square. When I differentiate it with respect to time, I get this as I by 2 into 2 omega into d omega over dt, and this d omega over dt is defined as the angular acceleration I omega alpha. So what we have here, this power which we obtain by differentiating the work done, and this power we are getting by differentiating kinetic energy of rotation. If we equate the two of them, I get that torque into omega is equal to I omega into the angular acceleration, and naturally because omega and omega cancel out, so I am left with torque is equal to I into alpha. This is an expression that says that the torque is equal to moment of inertia about the given axis multiplied by the angular acceleration possessed by it. This has got the similarity with the Newton's second law. So F is equal to ma. So the counterpart of the Newton's second law in the rotatory motion, rotational motion, we can write it torque is equal to I alpha. Next, in the next lecture, I will discuss the angular momentum and the conservation of angular momentum, etc. I'll take up in the next lecture, in the next outing. So, thus far, where I will use this equation, this diagram also, just to understand the thing. By the way, to the question that was asked by Mr. Tawseef Ahmed, I want to tell you that this R which is taken over here, there are two things from O to C and from C to P. Okay, these two segments are there, and by the addition of vectors, subtraction of vectors law, I can see, so it doesn't matter whether this O is here or this O is here, or you take the origin of the coordinate system that we have anywhere. So this is, I wind up also with the answer to Mr. Tawseef Ahmed, and I want to thank him for correcting me, and I stand corrected, and I hope I get more opportunities to stand corrected. So thank you very much. Please remember, like Mr. Tawseef Ahmed, you question and we will answer. Okay, so subscribe to the channel, and we will come up soon with the angular momentum and its conservation as is done for a rotating body about an axis of rotation. Thank you very much.